Welcome back, everyone. Today is kind of a fun day. Last time I told you that Gibbs free energy was one of the most important concepts in all of chemistry, and today we're going to show that. I've selected a few ways that Gibbs free energy is related to different topics we study throughout the year. This is by no means an exhaustive list, but these are some ways that I think it's easy to relate energy to the topics. Remember that Gibbs free energy is delta G equals delta H minus T delta S. So your can-dos are, by the end of this lecture, you can explain how Gibbs free energy is related to entropy of mixing, solutions and solvation, equilibrium, colligative properties, acid-base strength, redox, and also I can find delta G when given current concentrations, temperature, and delta G naught, and use it to predict which way a reaction will proceed. So don't worry, throughout the lecture today, most of this material will not be on the unit exam. It will be covered when we study the other topics. The one thing that I will probably put on the exam is the last topic about finding delta G and predicting which way a reaction will proceed, and I'll point that out when we cover it. The first thing that we're going to talk about is entropy of mixing. On the left side, we're not going to have any mixing yet. We're just going to talk about a gas expanding into a larger volume. We talked about this on the first day. So imagine that we have a container divided in half and all the gas molecules are on the left side and the right side is a vacuum, which doesn't necessarily mean suction, it just means that there are no gas molecules on the right side. And then we remove the barrier. Because all the gas molecules are moving, they will spread out on their own to be evenly distributed throughout the whole new volume. And one way that we can describe this is that they were real concentrated because they were really close together in the top picture, but then when they spread out, they're dilute. So you don't have to have something dilute something else, like adding more water to a solution will dilute it, but you can just think of something spreading out as being diluted. And next to those pictures, where it says A and B, we have the energy level diagrams. And when we learned about entropy, we said that if something spreads out into a larger volume, that it has more energy levels accessible or available, and the molecules will start to occupy all those different energy levels. They can have different momentums, which allow them to occupy those levels. So when there's more levels for the same overall amount of energy, like in B, there are more levels than in A. And if we look at the height of the pink box in those pictures, that's the overall amount of energy. So the molecules have many more choices in B, and that's an increase in entropy, or positive delta S. Well, now let's look at the right side. This is mixing, and actually the way we can think about mixing is things expanding into the larger volume of each other. So imagine now in the top diagram we have red molecules on the left and blue molecules on the right. And we remove the barrier. And when they mix, they basically spread out into the new volumes. Dalton, the guy who had the Dalton's law of partial pressures that we learned when we studied gases, said that gases were a vacuum unto each other, which basically means that the gas molecules are so small and spread out that they don't really interact with each other if they're ideal gases when they mix. So basically, the left side red molecules, when they mix, they're just spreading out into the new volume, just like they did in the picture on the left side. And when the blue molecules mix, they're just spreading out into the new volume like they did on the right side. And there's not necessarily interactions between them, they're just spread out into a new volume. Both of the red and the blue molecules each now have twice as much volume to occupy. And so, as we see in the energy level diagrams, when they are unmixed and separated, the energy levels are further apart, so there are fewer available for the atoms or molecules to occupy. But in the lower picture, in B, when they're mixed, their energy levels are closer together, so they are more accessible to them, and that's an increased entropy. And we call this delta S mixing, the entropy of mixing, which basically just says that entropy increases because things are spreading out into each other, into a new volume, into a bigger volume. This picture talks about when we dissolve something. Like if we dissolved sodium hydroxide in water, the solution becomes very hot. But if you dissolve urea in water, the solution becomes cold. Why is this? Let's start on the left side of the picture where we see the orange solute molecules. And when a solute dissolves, the solid's molecules or ions have to be pulled apart from each other, where it says separated solute. They have to be pulled apart so they can make room for the solvent when it comes in and surrounds it. So pulling it apart takes heat, which is a positive delta H, positive enthalpy, to break the ionic bonds, hydrogen bonds, dipole-dipole interactions, van der Waals forces, all of those intermolecular forces that are holding them together. The molecules of the solvent, the blue, also have to be separated to make room for the solute. This also takes heat energy. That's the positive delta H that you see in the picture in step 1 for both of them. For example, liquid water molecules have hydrogen bonds to 3 of their neighbors on average. These have to be broken for solvation to pull them apart. And solvation is the process of dissolving a solute. So then we go to the top of the diagram where it says separated particles, and they're going to now mix. And after the solute and solvent molecules mix, they form new intermolecular involvements, such as new hydrogen bonds, ion-dipole attractions, dipole-dipole interactions, and van der Waals interactions. And this causes a release of heat energy, or a negative delta H. So that's why we're going back down to energy level. When we have our solution and they're all mixed up, and you can see where it says step 3, that's a negative delta H. And if more heat was released from the new interactions between the solute and solvent than it took to pull them apart, then the overall process is exothermic. It has a negative delta H of solution, and the solution heats up. So this picture is an example where we have a negative delta H solution. You can see that the energy level of the solution down at the bottom is lower than the energy level of the solute plus the solvent on the left side. This picture shows the opposite. This would be more like urea. And here you can see that it's taking more heat to break the bonds and turn them into separated solute and separated solvent, that separated particles, than is released when the solute and solvent form intermolecular forces between each other in solution. So this has a positive delta H of solution because the ending energy level is higher than the beginning. And so this would be an endothermic process. So this would be when the solution becomes cold and it absorbs heat from the surroundings. If this whole process is taking energy, like why is it even happening at all? Why would something dissolve at all that's an endothermic solute? Well, because remember we talked about that enthalpy is not the only driving force. We have our Gibbs free energy up in the corner here. So your Gibbs free energy of solution is the delta H of solution minus the T delta S of solution. So we also have to talk about entropy of solution, and this is that entropy of mixing that we were talking about. So on the right side, you can see that solute and solvent have a lower level of entropy than when they're all mixed up at the top, and that causes a positive delta S of solution. And if we go back to our previous picture, the negative delta H, or the exothermic solution that became hot, we still see that there is a positive delta S of solution. So when things are mixing, they're increasing entropy. And for both of these create a negative delta G of solution, and so it becomes soluble. Here, both the negative delta H of solution and the positive delta S of solution increase solubility. Here on the other one, the endothermic solution, we have to have the T delta S component, the entropy component, outweigh the enthalpy component to give us a negative delta G of solution to make the solute soluble in that solvent. This slide shows a reaction coordinate, which is really just a graph of over time what happens to the energy of the reactants and products. We learned that a reaction is spontaneous when delta G is negative. in this general reaction of A plus B goes to C plus D, on the left graph we have the G naught of the reactants A plus B, and that's at this level of energy right here. And as the reaction proceeds in time, the final G naught of the products C plus D is lower. So the distance here is the delta G, and it is less than 0, so we would say this is a spontaneous reaction. The distance here as the energy goes up, that's the activation energy. We haven't talked about that yet. We will talk about that a lot in our chapter on kinetics. The picture on the right is of an endergonic reaction. That's when delta G is greater than 0, and we can see that the G naught for the reactants A plus B is lower than the products C plus D, so delta G is positive or greater than 0. Two NO2 molecules will dimerize to the molecule N2O4 in the reaction that's listed. This reaction is spontaneous because delta G naught is negative 2.8, but you would expect that if you started with 2 moles of NO2, that by the end of the reaction all would be converted and you would have 1 mole of N2O4. But if you put it in a sealed container, some but not all of the NO2 will become N2O4. Why not? In a closed system, if the reactants and products are in the same phase of matter, it will never go to completion. It will reach equilibrium. First, let's find out how much N2O4 will be made. The equilibrium constant, KEQ, is defined by G naught. It's defined by the Gibbs free energy. And you can see in the equation here that KEQ equals e to the negative G naught over RT. And you remember from our equilibrium chapter that KEQ is also the concentration of the products over the concentration of the reactants, and we square the reactants here because the coefficient is 2 in the equation. We just leave N2O4 to the 1 because there's only 1 mole made in the equation. If you plug all those numbers in, you find that the equilibrium constant is approximately 3. During the equilibrium unit, we solved problems such as these. If we put 2 moles of NO2 in a 1 liter sealed container and wait until equilibrium, what will be the final concentration of NO2 and of N2O4? We already know our equation, and we're going to make our ice table. So we start with the 2 molar NO2, and we have 0 molar N2O4, and then we're going to write our change, so we're going minus 2x because the coefficient is 2, and plus x because our coefficient is 1. And so we finally end with 2 molar minus 2x, and on the right side with x. We go ahead and plug those results into our KEQ, and we'll have to solve the quadratic formula. And finally we find that x equals 0.75. We're not done yet until we put the x's back into our equations, and we can find that there's 0.5 molar NO2 and 0.75 molar N2O4. So you can see that it's definitely not all converted to N2O4. So why do we only get 0.75 molar N2O4 and we're left with 0.5 molar N2O2, despite the fact that the reaction has a large negative delta G? It was negative 2.8 kilojoules per mole. This goes back to our entropy of mixing. This is so important when it comes to understanding equilibrium. If there were no reaction at all and we had just added NO2 and N2O4 to a container, we would have a positive delta S of mixing, just like when we saw the picture of the gas molecules, the red ones and the blue ones mixing. So imagine the red ones were NO2 and the blue ones were N2O4, and they just are mixing together. They're not reacting at all. And you can see that they would have an increased entropy. Let's look at the graphs on the bottom. We're going to say that the x-axis is what percent of it is N2O4, and the graph on the left is delta S of mixing, and the graph on the right is delta G of mixing. And you can see that when it's about 50% N2O4, that's when you would maximize entropy. And when you maximize entropy, when you maximize positive delta S, that's when you have the greatest negative delta G. This driving force pushes NO2 not to react and convert to N2O4 so that there can be a mix of the two molecules. If all the NO2 gets converted to N2O4 in a reaction, the system will miss out on the entropy of mixing. This tug of war between the reaction delta G, that's the difference between the G naught of formation of the reactants and the products, and the mixing delta G means that all reactants will never be converted to products as long as they're in the same phase. Let's look at the graph on the right. Line 1 is a straight line that shows how delta G would change as the reaction progressed if we could somehow keep the reactants and products separate. So like every time a molecule NO2 dimerized to N2O4, it was like taken out and kept separate. And there we prevented mixing. Whereas line 2, the green line, the U-shaped one going down and then coming back up, shows what happens to the total delta G when that U-shaped mixing curve that we saw on the left side mixes with that straight line, the line 1. The lowest point, the purple square, which produces the largest possible negative delta G, is the equilibrium point. And it so happens for this that this is where there are 0.5 moles of NO2 and 0.75 moles of N2O4, like we just figured out in our ice table. Let's note that if we had stayed at the 0.5 moles of NO2 and the 0.75 moles of N2O4, we've only gone part way down on our straight line, on our line 1. So we haven't made all the negative delta G possible we could if the reactants went all the way to products. It produces a smaller negative delta G from the reaction than if it had gone to completion. However, we made up this from the delta G due to the delta S of mixing, and that's this distance right here between line 1 and line 2. Next, we have our 0.5 moles of NO2 and our 0.75 moles of N2O4 at equilibrium in a 1 liter flask, and we add 1 mole of N2O4. What will happen? Well, remember our guy Le Chatelier? He defined a phenomenon, and he described things at equilibrium, and he said if you put a stress on that equilibrium, everything will shift to relieve that stress. So here we put in 1 mole of N2O4 stress on the right, and the equilibrium will shift to the left, which will produce more NO2 and relieve the stress. Simple enough, but what about this example? This time we put 1 mole of NO2 and 1 mole of N2O4 into a 1 liter sealed container, and we wait until equilibrium. What will be the final concentration of each? So let's try our ice table. We put the 1 molar on each column, but then we look at our change. Is it minus 2x or is it minus x? Are we going to the left? Are we going to the right? How do we possibly know? We don't know which way it will take place. We have to use the reaction quotient Q, which has the same format as KEQ, but describes the current conditions, not at equilibrium. So that's the Q that's in the red box on the left. And if we plug in the numbers, the 1 mole and 1 mole, we find that Q equals 1. And in the equilibrium chapter, we learn that if Q is less than KEQ in the purple box, we shift to the right. Now we know the direction to change for our ice table, so that will be the minus 2x and plus x. And our final concentrations, once we plug them into our KEQ formula in the brown box on the right, we find that x equals 0.2. And when we plug that in for x, we find that the final concentration of NO2 is 0.6 molar, and the final concentration of N2O4 is 1.2 molar. Memorizing that if Q is less than KEQ, the reaction shifts to the right, and if Q is greater than KEQ, the reaction shifts to the left, is super useful, but where does this come from? Well, we're talking about Gibbs free energy, so it all comes down to Gibbs free energy. And this equation here, for the general reaction, A plus B goes to C plus D, we have the formula that delta G equals delta G naught plus RT the natural log of Q. And we defined Q to look just like the equilibrium constant, but with current concentrations. And we have to remember that when we have delta G naught only refers to the conditions at equilibrium, at standard atmospheric temperature and pressure. And you calculate delta G naught, not by doing an experiment, but from the delta G formation in tables. But delta G is right now. This is based on the experiment you're actually doing with your current concentrations that you found in Q. Let's revisit both of our problems using our new equation. So we have our 0.5 moles of NO2 and 0.75 moles of N2O4 at equilibrium, and we add 1 mole of N2O4. What will happen? Well, we knew from Le Chatelier it'll go to the left, but let's prove that with Gibbs free energy. So we have our equation, the delta G equals delta G naught plus RT ln Q. And we put in all our numbers, and we find that delta G is positive 2021 joules per mole. So the reaction is spontaneous to the left because delta G is positive. In our other problem, where we put 1 mole of each and then didn't know which way to go, we had to find the Q. Let's also use our delta G naught equals delta G plus RT ln Q. And in the green box, when we plugged in all those numbers, we find below that delta G equals negative 2,800 joules per mole. Since delta G is negative, the reaction spontaneously goes to the right. All right, now we understand the why behind the rule. If Q is less than KEQ, the reaction proceeds to the right. When Q is less than KEQ, it will give a negative delta G. Let's just verify one more thing. After part C comes to equilibrium, we found that the concentration of NO2 was 0.6 molar and the concentration of N2O4 was 1.6 molar. What's delta G right now at equilibrium? Well, let's plug it back into our delta G equals delta G naught plus RT ln Q formula. And when you add and when you put all the numbers in, you find that delta G is approximately 0 joules per mole. And this is super key. At equilibrium, delta G equals 0, and delta G naught equals negative RT ln KEQ. So when Q is less than KEQ, the reaction shifts to the right because delta G is negative, and when Q is greater than KEQ, the reaction shifts to the left because delta G is positive. That was the one thing that will probably be on your exam, the delta G equals delta G naught plus RT ln Q. Let's move on now to our colligative properties. So solve the following examples using the freezing point depression and boiling point elevation formulae that we learned in previous units. We're going to dissolve 58 grams of sodium chloride in 1 liter of water. What temperature will it freeze at? And we're going to dissolve 58 grams of sodium chloride in 1 liter of water. What temperature will it boil at? So put it on pause and solve those problems. We found that the freezing temperature is minus 3.72 degrees Celsius and the boiling temperature is 101.2 degrees Celsius. How can we use entropy to explain the colligative properties? That a non-volatile solute causes a solvent's freezing point to be lowered, but boiling point to be elevated. We usually focus on the solute in solutions, like we'll focus on the sodium chloride. But this time we're going to focus on the solvent. The solvent is diluted by the solute, or you could think of the solvent spreading out into the volume of the solute. Again, just like a gas expanding into a bigger volume, this opens up more places and momentum for the energy carrier solvent molecules, making their energy levels closer, so there are more accessible energy states and thus increase entropy. Remember that freezing and melting and condensation and boiling are equilibrium between two phases. The temperature is the same for the ice that is at the point of melting as for the water that is at the point of freezing. The same holds true for condensing and boiling. Since temperature is proportional to average kinetic energy, the phase change will happen when the energy is similar. Since the solution's energy levels are closer than that of the pure liquid, melting will take less energy for the number of available energy levels to be equal in the solid and solution versus the solid and pure liquid. Boiling will take more energy for the number of available energy levels to be equal in the solution and the gas versus the pure liquid in the gas. Let's move on to acid and base strength, aka the fall of the proton. For an example, you have one solution of sodium chloride and a second solution of sodium phosphate. To each solution, you start to add HCl. What will happen in each solution? The key to remember is that the proton, or the H plus ion, will fall to the stronger base. But how do we decide what's the strongest base? So I absolutely love this super awesome chart that I modified from Dr. Stephen Lower. And the left side of the chart talks about the delta G naught that results when a proton is transferred from an acid on the left to a proton sink on the right, which is a base. The more distance the proton falls, the greater the negative delta G, the more spontaneous it is. So in our example, we were adding acid to our sodium phosphate solution. Let's go to the one with the green check mark. And so a hydrogen ion will be transferred from water. So on the top line, we go from H3O plus to water, and then we fall in the diagonal line to phosphate, and then it goes back to the left like a Z. So you'll make HPO4 2 minus. And that has a negative delta G of negative 72 kilojoules per mole. And if you followed that on the left side of the diagram, you would look at the numbers and you could see that the distance was 72 kilojoules per mole. The fall and the negative delta G help us explain why adding acid to sodium phosphate will form HPO4 2 minus. Now let's talk about the one with the red X. That's adding acid to a sodium chloride solution. So in that example, we would have the hydrogen ion being transferred from water to the chloride and making HCl, but that would be a delta G naught of positive 40 kilojoules per mole. So adding acid to the sodium chloride will not cause HCl to form because that would result in a positive delta G, or the proton going uphill. This is why HCl is a strong acid. It completely ionizes to H3O plus and Cl minus and does not form HCl ion pairs. H2O, water, is a stronger base than the chlorate ion, the hydrogen sulfate ion, the chloride ion, and the nitrate ion. So delta G naught is negative or spontaneous when HClO4, H2SO4, HCl, and HNO3 give their proton to water. So these acids only exist in water in dissociated forms. They won't form ion pairs. And you can see that they have downhill arrows on all the transfers to water. But this chart would imply that weak acids, such as acetic acid, would never dissociate and give its proton to H2O to form H3O+. But we know from our acid-base unit that this is not the case. So if it's a positive delta G process of the proton going uphill, where does this energy come from? Well, first, let's find out how much the acetic acid actually dissociates. So let's calculate the concentration of the hydrogen ion, or the H3O+. We'll use our Ka formula, which is our KeQ formula, and if you plug everything in, you get that the concentration of H3O+ is 1.4 times 10 to the negative third molar, or 1.4 millimolar. So there is definitely some dissociation. And let's just verify that our delta G naught would be positive with our negative RT ln KeQ equation. And we see when we plug in the numbers that delta G naught would be positive 26 kilojoules per mole. If we would have just used our diagram, we would see that the proton would be going uphill and that the distance would be approximately positive 26. So where is this energy coming from, this positive 26 kilojoules per mole? Well, it's from random collisions of high momentum. They provide the energy needed for some of the acetic acid to dissociate. Final example for acids, you have a solution containing KCN and K3PO4, so you start adding HCl. What will happen? Well, the proton's still going to fall, but it will fall to the stronger base first. So we can see that PO4 is below Cn minus, and so PO4 is the stronger base. The proton will fall a stronger distance, so most of the PO4 molecules will make HPO4 2 minus before the Cn molecules take the proton to make HCN. You can see that the delta G naught is greater at negative 80 for the top reaction versus negative 60 for the bottom reaction. We just talked about acids and bases and how protons are transferred, and they fall down to give a large negative delta G. Now we're going to talk about fall of the electron, and when electrons are transferred, that is oxidation or reduction. We learned the activity series of metals and how they are related to cell potentials. That's E naught, cell. The tool modified from Dr. Lower is another useful tool to help us understand redox within the frame of Gibbs free energy changes. So for an example, you build a battery with a zinc electrode in a ZnCl2 solution and a copper electrode in a copper 2 chloride solution. Will the reaction be that the zinc ion gets reduced and the copper ion gets oxidized, or vice versa? So the key to remember here is that the electron will fall to the stronger oxidizing agent, or the stronger zinc. So if we look on the left with the green check mark, the zinc will get oxidized and the copper will get reduced. How is cell potential related to delta G naught? Well, using the battery we just built with zinc and copper, let's find each one. So we decided that copper gets reduced and zinc gets oxidized, and we have our standard reduction potentials that we found from our tables. We end up getting a positive 1.097 volts. That would be the voltage of our battery. Well, there's the Nernst equation, N-E-R-N-S-T, which says that delta G naught equals negative NF E naught, or E naught equals negative delta G naught divided by NF. And F is called the Faraday constant, and it is the charge of 1 mole of electrons, which is 96,485 coulombs per mole. Let's remember that one definition of our Gibbs free energy is the amount of non-pressure volume expansion work, such as electrical work, that can be done. So the Nernst equation calculates this work and changes it to voltage, which is often easier to work with when using electrical equipment. So when we plug in our numbers, we find that the delta G naught is negative 212 kilojoules, and that should be spontaneous. Remember, our cell potentials are positive when they're spontaneous, and the delta G naught is negative when it's spontaneous. If we had used our diagram from Dr. Lower and followed the numbers on the sides, we would also get the same results. I know this was a lot, but hopefully it showed you the importance of this unit. Let's review that we talked about our Gibbs free energy and how it's related to entropy of mixing, solutions and solvation, equilibrium, colligative properties, acid-base strength, and redox. And we talked about how delta G is, for current conditions, it will tell you whether your reaction will be spontaneous, and it takes into account temperature and delta G naught, which is what we find from tables from the Gibbs free energy of formation. And we use our delta G to predict which way a reaction will proceed. So that's it. The energy and entropy unit is concluded. We see that the Gibbs free energy is king, and it pretty much determines so many other things in chemistry. I hope that you enjoyed this unit, even though it's really difficult. I hope that you enjoyed the depth and the explanations. I wish that someone would have presented it to me this way when I first learned it, because to me it was just kind of some magic that entropy should increase and there's this Gibbs free energy, but no one really related it to me as far as what's going on. So thanks for all your hard work during this unit.